Welcome to my presentation on the Dirac equation in the T0 model. This visualization shows how we maintain the core of the Dirac equation while extending it in two complementary frameworks. At the top you see the standard form which remains fundamentally valid, providing descriptions for particles with half-spin and predicting antiparticles. Below that are our two extensions, on the left, the T0 model with its intrinsic time field T of xt that modifies dynamics, and on the right, the extended standard model with its scalar field theta. Both approaches derive all constants from energy principles, connected through a logarithmic relationship. At the bottom you can see our remarkable verification through the electron G2 factor, where our prediction matches experimental measurements within just 0.03 standard deviations, all without any parameter adjustments. Integration of the Dirac equation in the T0 model, energy-derived constants lead to precise predictions without free parameters. This presentation introduces a groundbreaking approach to theoretical physics. The key insight that drives our research is that all constants can be derived from fundamental energy principles, eliminating the need for free parameters and resulting in highly precise predictions that match experimental observations. For detailed derivations, proofs, and comprehensive analysis, please refer to the original document linked in the source reference. The Dirac equation stands as a cornerstone of relativistic quantum mechanics. It elegantly unifies quantum mechanics and special relativity for particles with half-spin, with its 4x4 matrix structure accounting for electron spin and famously predicting the existence of antimatter. However, integrating this equation into the T0 model presents three key challenges: deriving the 4x4 matrix structure from T0 principles, formalizing the spin statistics theorem within the T0 framework, and implementing QED precision calculations comparable to conventional approaches. We have already made significant progress in integrating the Dirac equation into the T0 model. Our achievements include extending the Schrödinger equation with a dynamic time field as shown in this equation, and developing conceptual frameworks for spin and antimatter. To address the remaining challenges, we are using the extended standard model as a bridge. The ESM retains relative time and constant mass while introducing a scalar field theta that is logarithmically related to our intrinsic time field. This familiar framework eases mathematical development and allows results to be translated via the logarithmic relationship. In the extended standard model, we have modified the Dirac equation to include the influence of the scalar field theta. The equation takes this form, with an additional term in the derivative that accounts for the field influence on fermion propagation. This modification comes from a field redefinition that induces a transformation of the derivative. Physically, this means fermions propagate differently in regions with strong theta gradients. Importantly, this same field appears in our modified Einstein equations, creating a consistent theoretical framework across quantum and gravitational domains. One of our key challenges is deriving the 4x4 matrix structure of the Dirac equation. This structure naturally predicts particles with half-spin and antimatter through the gamma matrices that satisfy the Clifford algebra. We are exploring three promising approaches: a geometric approach where the field defines a metric leading to a Clifford algebra, an algebraic approach using quaternionic structure, and a field-theoretic approach where tensor products generate higher algebraic structures. In the T0 implementation, we have developed a generalized Dirac equation with time field dependence as shown here. The spin statistics theorem links particle spin to quantum statistics, explaining why fermions and bosons behave differently. In the ESM, we have preserved this relationship through a three-step derivation: first, confirming that theta transforms as a scalar, maintaining Lorentz invariance; second, showing that our modified propagator preserves microcausality; and third, demonstrating that anti-commutation relations remain consistent during quantization. In the T0 model, this theorem reflects how the intrinsic time field interacts differently with particles of different spin values, while preserving the core spin statistics relationship despite field modifications. Our energy-based foundation successfully preserves these fundamental quantum properties. We have extended quantum electrodynamics to include our scalar field, as shown in this Lagrangian. The T0 model offers a significant advantage here: all parameters, including kappa and coupling constants, are derived from energy principles, with no free parameters to adjust. This presents a stringent test of our theory, as precision serves as validation rather than calibration. This contrasts sharply with the standard model, which contains 18 or more freely adjustable parameters, and most extensions that introduce additional free parameters. Our fixed parameter approach moves directly from energy principles to precise predictions without adjustments. The acid test for our theory is the precise prediction of the electron anomalous magnetic moment. Currently, there is a small discrepancy between experimental measurements and standard model predictions of approximately -0.88 plus -0.36 times 10 to the -12. Our T0 model contribution, calculated from first principles, yields -0.89 plus -0.05 times 10 to the -12. This remarkable agreement, within only 0.03 standard deviations, emerges naturally from our theory without any parameter adjustments. Even more impressive, we are using exactly the same parameters that work in the gravitational sector, demonstrating the consistency of our energy-derived constants across different physical domains. In conclusion, we've shown that all constants in both the T0 and ESM models can be derived from energy principles, eliminating the need for free parameters while delivering precise predictions. Although the mathematical formulations differ based on different ontological foundations, they converge to the same physical reality. This approach transforms how we validate theories, through prediction rather than calibration to experiments. Looking ahead, we plan to apply these principles to the μ(G)(2) anomaly, extend our work to other precision QED tests, and explore implications for a unified theory. When constants are derived from energy principles, theories naturally converge to precise predictions.